Okay, this little movie is about multiplying binomials, something we call binomial expansion, and about a really wonderful tool to do this sometimes onerous task. So first of all, a binomial means two terms. So we could express a general binomial as a plus b, where a could be anything. It could be the square root of 2 times x cubed times z, or it could just be 5. A could be anything and b can be anything. And here are some examples of very common binomials that you've encountered. X plus 2, see, two terms separated by a plus or a minus. 17x minus 2, a minus 3, or we could write it as negative 3 plus a, because we know that the order doesn't matter in addition. Addition is commutative. Now, the binomial itself is not really a scary object, just two terms. But once we have to multiply it by itself 2 or 4 or more times, it can become an extremely tedious and error-prone task. So we're going to look at x minus 3 cubed. And the standard way to do this would be to multiply out. So x minus 3 cubed means x minus 3 times x minus 3 times x minus 3. And we can kind of group these because we don't want to multiply all three in one shot. That requires a special algorithm. Instead, we'll multiply the second pair first, expand it to a trinomial, x squared minus 6x plus 9. We still have to multiply by x minus 3. So we multiply the whole thing, the whole trinomial by x, and the whole trinomial by minus 3, and then we add everything together. X times x squared is x cubed, x times negative 6x is negative 6x squared, and x times 9 is 9x. Now we do the negative 3. Negative 3 times x squared. Negative 3 times negative 6 is positive 18. Positive 18x. And negative 3 times positive 9, negative 27. We add up all the like terms, and we get x cubed minus 9x squared plus 27x minus 27. Imagine if this were x minus 3 to the 6th power. We would have so much more multiplication to do. And at every step, multiplying positives by negatives or distributing, there's a chance of making an error. Anyone could do it. Now, instead of using this method, we could use something really special. We could use Pascal's triangle. Now, I have to tell you, I'm going to show you Pascal's triangle, and I'm going to show you how to create it. And that part is really simple. But I'm only going to discuss one small secret that Pascal's triangle has. There are many, many more. Here it is. Here is just the very top. We could go on and on and on. But the first few rows of Pascal's triangle are created this way. All you really have to remember are the 3 ones at the top. Every element, like this 2, is the sum of the 2 parent elements above it on the left and on the right. So that's true here too. This 1 is the sum of nothing on the left and 1 on the right. And all these 1s are like that. But 2 is the sum of 1 plus 1. And this 1 is the sum of 1 plus nothing on the right. And when we get down to the next row, we have more to see. We get the 1s, but 3 is the sum of 1 plus 2. And this 3 is the sum of 2 plus 1. And the 1 is the sum of 1 plus nothing on the right. And so on. The 6 is the sum of 3 plus 3. You could create this triangle and go on forever. And this actually has, I'm fixing the spelling there, this actually has the key to so many, many questions, but it also holds a solution for binomial expansion. Each row here, and you can look at this diagonal here to tell you what exponent. The first row gives you a plus b to the first power. It doesn't really give it to you, but it really does. The second row gives you a plus b squared. The third row gives you a plus b to the third. So that's what we're going to look at here. So what part is it giving you? Well, you know it's a plus b. And these are the important coefficients of the terms. So the first one's really simple. We have the red 1 times a to the first power, literally b to the 0 power here. And then we add plus b times the last one to the first power, a to the 0 power. This is not really explaining the algorithm to you, but it's necessary to just complete the picture. Now let's look at a plus b squared. We know it's this row because the 2 is the second element. And we're going to expand this by starting with the highest power of a we're going to get, which would be a squared, and the lowest power of b to the 0. So we have a squared b to the 0. And the coefficient of that is this red 1, a squared b to the 0. Now the exponents change by having the a exponent go down by 1 and the b exponent go up by 1. So a squared becomes a to the first, and b to the 0 goes up to b to the 1. And the coefficient is the 2. 2ab. And then finally, we do the same exponent thing. It's just a pattern. The 1, which is an exponent on a, goes down to 0. A to the 0 is really just 1, so the a's disappear. And the 1 on the b goes up to b squared. And what's the coefficient? The 1, the blue 1. So we get what we would expect, a squared plus 2ab plus b squared. We don't really see the value of this until you do a plus b cubed. Now you see the real benefit of Pascal's triangle when we have a plus b cubed. We know we're using this row of the triangle, the 1, 3, 3, 1, because the second number in that row is 3, and it's a plus b cubed. And we follow the pattern. These are the coefficients, and the exponents go exactly as they did before. A to the highest power, the exponent we're using in this expansion, so a cubed, b to the lowest power, b to the 0. 1 times a cubed, b to the 0. And now everything follows from this. The exponent for a goes down by 1, a squared. The exponent of b goes up by 1, b to the first. And the coefficient is this green 3, 3a squared b. Now for the next term, the coefficient is the same. It's now the pink 3. The exponent of a goes down by 1 to a to the first, and the exponent of b goes up by 1 to b squared. 3a squared b plus 3ab squared. Finally, the exponent of a goes down by 1 to 0. A to the 0 is just 1. The coefficient is the blue 1, and the exponent of b goes up by 1 to b cubed. So we get a cubed plus 3a squared b plus 3ab cubed plus b cubed. And now we can just apply that to our particular x minus 3 cubed. So what we're really doing is using a cubed plus 3a squared b plus 3ab cubed plus a to the 0, really 1, b cubed. And we have to first say what's our a, what's our b. We should just kind of write that here. A equals x in this case. And b equals negative 3. Word wants to make that a capital B, but we're using a lowercase b. So we plug these in to our formula. We have a cubed, that's going to be x cubed. We have 3a squared b, 3x squared times negative 3. That's going to be negative 9x squared. Then we have 3x to the first power, a to the first power, times negative 3 squared, that's 9. 3 times 9 is 27, 27x. Finally, negative 3, the b cubed, and we get negative 27. We really do this in 2 simple steps. As you get good at it, you can go right to this step. You don't think about a plus b's. You just use the row in Pascal's triangle to find your expansion. Remember, we can compare just finding the pattern in 1 or 2 steps to multiplying out, which gets more and more and more complicated as the exponent grows. Because now you can use the triangle to find the 5th power of x minus 3 or the 7th power of x minus 3. And the triangle is easy to remember.